Section 2D is about fundamentals of probability, but it's really about one in particular, which is this idea of what you can do if you have a compound event made out of multiple outcomes, but all the outcomes in the sample space have the same probability. And there are other fundamentals of probability as well. One of them is down here, because this actually comes into play a little bit, that for any event A, the probability of A has to be between 0 and 1. So probabilities are typically written as decimals, not as percents. So an event with probability 0 is one that never happens, and an event with probability 1 is one that always happens. So yeah, you'd have to be within that interval, right? Something can't happen less often than never, and something can happen more often than always. So sure, that's got to hold up, but this actually does come in handy in a little bit. So okay, what about this equally likely outcome business? Like, where is this going to come up? Well, the easy examples would be things like flipping a coin, right? Because you think probability of heads, probability of tails, both going to be 1/2. Rolling a single die, that would work. Picking a card at random out of a traditional 52 card deck, because you can always differentiate the cards, right? If you specify the suit, and then if it's a number or what kind of face card, or if it's an ace, right? You can differentiate all the cards from all the other cards. So what happens if you have equally likely outcomes? I just wrote this with an n generally, so n is some positive integer, right? If you're rolling a single die, n is 6, right? Because you could roll a 1, 2, 3, 4, 5, or 6. If it's pulling a card randomly out of a deck, n is 52, right? That's the idea there. And then event A, so the term for an event with multiple outcomes, or one that consists of multiple outcomes, is a compound event. So like a simple event is just one outcome. So like if you were rolling one die, rolling a 2, that's a simple event because that's just one outcome. But rolling an even number, that's a compound event because it would involve 3 possible outcomes, 2, 4, and 6. So this is really for compound events, but it would work for simple events too. It would just kind of be extra work for simple events. I guess first of all, why does this part work? That the probability of any individual outcome is 1/n. Well, it works basically because you have to get the 1 when you add up all the individual probabilities, right? Like if you were going to roll a single die and said, okay, well then there n is 6, so the probability of rolling a 1, rolling a 2, rolling a 3, and so forth are all going to be 1/6. Sure, because you have 6 possible outcomes, and if they all have a probability of 1/6, then 6 1/6 added together, or just 6 times 1/6, is 1. And you have to have one of the possible outcomes happen, right? Like if you're rolling a single traditional 6-sided die, you can't roll a 7. And you can't roll an 11, and you can't roll a 19, and things like that, right? It's got to be 1, 2, 3, 4, 5, or 6. So then when you add up the probability of 1, 2, 3, 4, 5, and 6, that should add up to 1 because one of those things has to happen. Like if you made an event that was equal to the sample space, just getting a 1, 2, 3, 4, 5, or 6, that probability's got to be 1. And that is actually where this comes from. But knowing that this would have to happen, or at least if we have one of these situations where we're going to have the equally likely outcomes, then this has to happen. Then for some event A that consists of multiple outcomes, then really what you end up with for the probability of A would just be the number of different ways that A could happen, which would be the number of outcomes in it, divided by how many outcomes are in the sample space, which we said was just lowercase n. So to make this a little bit more concrete, what if we rolled one die? Then the sample space is 1, 2, 3, 4, 5, and 6, and all 6 outcomes are equally likely. So in other words, the probability of rolling a 1 would be equal to the probability of rolling a 2, and so forth, probability of rolling a 3, 4, 5, and 6. They're all going to be 1/6. And so then what if event A isn't just one single outcome? What if it's multiple outcomes, something like this? So what if the event A is rolling a number less than 5? You could say, okay, well then, and I kind of wrote this out the long way, but you could say, well, what outcomes in the sample space are going to satisfy that? They're going to satisfy being less than 5. It's 1, 2, 3, and 4, right? So we can say, all right, well then the probability of A would be the probability of rolling a 1 plus probability of rolling a 2 or a 3 or 4. So it's 1/6, 1/6, 1/6, 1/6, all added together. And that's 4/6, which reduces to 2/3. That's kind of the long way of thinking about it. The shorter way would be to say, well, there are 4 outcomes in the sample space that are going to be less than 5. So we say there are 4 outcomes in A, 6 outcomes in the sample space, 4 divided by 6, which is 2/3. Right? That's the fast way. So that's where this comes in handy. It kind of shortens up some of the algebra a little bit. And that's kind of the idea with these examples here. So this first one, if a 20-sided die is rolled, right, a big board game thing, right, Dungeons and Dragons, I guess, would have initially popularized it, but it's in other stuff. It's even in the sports ones, right? It's in like Stratomatic baseball and hockey and stuff too. But anyway, with a 20-sided die, what would be the probability of rolling a prime number? Okay, well, then based on the formula up above, the thing that we really want is we want to know the number of prime numbers between 1 and 20, right? And then we can just say, okay, that's our numerator, 20, the number of outcomes in the sample space, that's our denominator, and that should do it, right? So then we got to figure out the prime numbers between 1 and 20 and then just count them up. I think that's the best thing to do. So the prime numbers between 1 and 20. And there are prime number questions in the homework, so just don't forget about 2. That's easy to forget because it's even, right? But 2 is a prime number, and then so is 3, so is 5, so is 7. 9 isn't, but 11 is. 13 is. 15 isn't, but 17 is, and 19 is. And there are 8 of them there, right? So what we've got is we've got 8 prime numbers between 1 and 20. And so what that means is then the probability of rolling a prime number, what we had is that we had 8 different ways that could happen, right? We had 8 prime numbers, and there are 20 possible outcomes in the sample space. So 20 possible outcomes. And I guess usually you wouldn't write this with the words, right? You would probably just write it as 8/20. And then that's going to reduce because both of those numbers are divisible by 4. So that's going to reduce to 2/5. And that would be the answer. All right, next, let's see. All right, so I guess with part A here, with picking out a letter, it looks like it's kind of the situation where we think of Y as being like a vowel. All right, so we're going to pick a letter at random from the English alphabet, and we want to determine the probability that the letter is a vowel or Y. So I guess the first thing is how many letters that is. And it's 6, right? Because you get the 5 regular vowels plus the Y. So vowel or Y, that's 6 letters, right? So then that would imply that the probability of vowel or Y would be 6 out of 26. Right? Because you have 6 different ways for that event of vowel or Y to happen, right? A, E, I, O, U, Y. And then there are 26 letters in the alphabet, right? So our sample space is just the regular alphabet here. This does reduce, if you want to write that as a fraction of the lowest terms, would be 3/13. Or if you want to write it as a decimal, because sometimes the homework asks for your answer as a decimal, that's 0.231 to 3 places. Okay. That didn't seem so bad. And then what about the probability the letter is listed somewhere after G in the alphabet? The easier way to think about this is to say, well, A through G, that's the first 7 letters. So I say A through G, is 7 letters, right? G is the 7th letter. And so that means that there would be 26 minus 7, which is 19 letters after G, right? So all I did was I counted the opposite idea, right? Instead of after G, I counted up to and including G, just because that number was going to be smaller, right? That seemed like it would be simpler. And that idea of using the opposite to figure out your probability, that factors into 2F, which is about the complement, but we'll get there when we get there. For now, we can just think of it as 7 is easier to count than 19, I guess, right? It doesn't take as long. So the probability that you get something after G, it should be 19 over 26, right? Because there are 19 letters after G, so there are 19 different ways you can get one that's after G. 26 letters total, and let's see, that's about 0.731 to 3 places, if you want that one as a decimal. All right, next. This next one looks like it's going to be more complicated than it is, and it's because there are the 3 options instead of just 2. And then number 4 just looks crazy, and it's not. So these are going to be deceptively short, the best kind, right? When it's a nice surprise when they're short. So a mixture of candies contains 8 mints, 4 toffees, 5 chocolates. And if a person makes a random selection of one of the candies, find the probability of getting a mint, and find the probability of getting a mint or a toffee. All right. Well, I guess the first thing we need is the total number of candies, because that's effectively our sample space, right? You have mint number 1, mint number 2, mint number 3 up to mint number 8, and then toffee number 1, number 2 up to toffee number 4, and then chocolate number 1, chocolate number 2 up to chocolate number 5, right? So 8 plus 4 plus 5, that's 17. So we need that. So the total number of candies, it's 8 plus 4 plus 5, which is 17. We need that because that's our denominator pretty much. So for part A, the probability of mint, well, we've got 8 mints, right? So then this should be 8 over, I guess 8 mints. I'll write this one with the words. So 8 mints over 17 candies total. Stretch out this dividing line a little, right? So that's 8 over 17, right? If you just want to write it without the words, I think that's totally fine. I'm just kind of doing this to make it look a little more descriptive, I guess. And then as a decimal, that's about 0.471. And I think sometimes the homework asks for the decimals to 2 places instead of 3. I'm just so accustomed to doing it to 3 that it's almost like I just do it reflexively. But they may ask for 2. And I guess if they ask for 2, then that's a 0.47 instead of a 0.471, right? And then, let's see, B. So we'd have the probability of mint or a toffee. So we're going to have to add some stuff in the numerator this time. Right, so I guess I'll do this one in words too. So you have 17 candies total still. And then there are 8 mints, 4 toffees. That's what it says up there. So 8 mints plus 4 toffees. It's going to be 8 plus 4 over 17, which would be 12 over 17, which is about 0.706. Okay, so that one looks more complex because it's one or the other. But you can just add these together because there's nothing that could be a mint and a toffee, right? It's one or the other. And when that happens, you can just say, well, we got 8 of these, we got 4 of these, that's 12 total, right? So that's basically what you can do there. Number 4. All right, so a box contains 500 envelopes, of which one contains $1,000. 4 contain 500, 20 contain 100, 80 contain 50, 125 contain 20, 270 contain 10. If an envelope is selected at random, what's the probability the envelope contains less than $50? Okay, what I think we should do is just kind of pick out the scenarios that involve envelopes with less than $50 in them. So, less than $50. Let's see, 1,000 too big, 500 too big, 100 too big, 50 too big because we want strictly less than 50, not less than or equal to. But there are 125 with 20, so we'll put that down. So 125 have $20, and then 270 have $10. That's less than 50. So 270 have $10, and then if I add this up, then 125 and 270 is 395. Have less than $50. All right. So then the probability of picking out an envelope that has less than $50. Well, there are 395 of them with less than $50 in them. And then total, there's 500, right? It says it right up there. I guess you could add up the individual numbers and get the 500 back out, but there's no point in doing that work when it says 500 right off the bat. And then 395 over 500 is 0.79. And this doesn't need to get rounded off. Like dividing by 500, you get a nice terminating decimal, and that's what it works out to be. So I think that's it for the equally likely outcomes type stuff. This is about as involved as it would get because you have a bunch of extraneous information in here, right? The only pieces you really need are just like, okay, I need that 125 and that 270 because those numbers are smaller than $50. And I guess, yeah, that's about it, because with something like this, you got to sift through the information a little. But I think in this section, this is about as involved as they would get.